Hello. In this project, I'm gonna discuss about the algorithm that I have been working since a few weeks ago, and this algorithm is called tracking learning detection. And I'm gonna take a look at how this tracking framework work and what it can do for the tracking task. And the theory was proposed by Danik Kala, which was a PhD student at University of Surrey. And the theory algorithm has the following features. First, it's a real-time tracker for standard resolution 240 by 320, and it has the ability to handle object disappearing and re-entering in partial occlusion, which is a must for a robust tracker. And it also can handle certain level of scale and rotation, which is good. And all this work have been presented in this PAMI paper in 2012. And this is an overview of this algorithm. You could say this algorithm consists of three parts. Each part does its job individually, and finally they combine all the three parts together to get the final results. Let's say this algorithm has a tracking part and has a detection part, also has a learning part. And each part work individually and they provide supplemental information for another. For example, in a tracking algorithm, it gives out a fragment of the trajectory which can be used for learning, and the learning just generate training data for detection. And of course, the detection do the job of tracker relationalization, which is very important for the next success of tracking. And the detection also can do something for learning as well. So in the following slides, I'm gonna dive into the details of these three components. Okay, first let's take a look at the tracking component. The tracking, simply put, the tracking is doing a basic tracking job, just like every other algorithms to do the tracking. So the authors proposed improved optical flow method, which is called median flow. And basically, it's an algorithm based on Lucas Canada's optical flow, but it adds certain level of error estimation techniques. These techniques include forward-backward error estimation and the normalized correlation coefficient and failure detections. The author uses all these three all the three error detection techniques to improve the tracking results. Let's first take a look at what forward-backward error means. Well, forward-backward error means first you have your first frame at x hat t, and you track it to the xt plus 1, and you continue this process until xt plus k. And at this point, you do a backtracking from which is from xt plus k backwards to xt plus 1 hat and to xt hat p. And you're gonna have to calculate the distances between these two results. If this distance is larger than a certain threshold, we will determine that this tracker has failed because the distances were larger. If this distance is just close enough, so we can assert that this level has passed. And the next level is to do the normalized correlation coefficient calculation, which select two patches of the feature point, and you calculate their correlation. And this correlation has the capability of indicating how close the 2 points are. If the 2 points are very close and they almost represent the same object and same object feature space, so you're gonna determine that this point maybe is the real object you're tracking, which means the tracking trajectory is acceptable. And the next thing is failure detection was also designed in the whole process. And um, after the previous two stages, there are only a few points remaining. So all you have to do is to calculate the median of all these points. For example, you have maybe a dozen points left, and you calculate the median along x direction and along y direction respectively, and you get the median vector. And in order to validate whether this vector is valid or not, you're gonna have to calculate again the median between the vector you calculated and any of other uh, individual motion vectors. If this median value is larger than a certain threshold, such as in this implementation it uses 10 pixels, you're gonna determine that this is not a good tracking result. You're gonna have to discard it. So the tracking, I just finished talking about the tracking part. The next thing is detection, which is another important component in this TOD framework. In detection, first you're gonna have to do is to generate the scanning window, which is which contains the scale and information. For example, you can generate this scanning window with a step size of 1.2 and a horizontal step with 10% of width and a vertical step of 10% of height. And also, you're gonna have to determine the minimum bounding box size should be larger than 20 pixels. Otherwise, definitely you don't want to do smaller than 20 pixels. And when you have the scanning window generated, all you have to do is to go through this cascaded detector classification process. The first step is you're gonna have to go through the patch variance, which is the simplest one. And this stage, you're gonna have to reject certain patches and pass the remaining patches to the second stage, which is ensemble classifier. It's gonna do further classification and rejects a bunch of the patches again, and the remaining ones continue to go to the third stage, which is one nearest neighbor classifier. And when you have gone all the three stages, the remaining points, the remaining pixels are accepted. So in the next slides, I'm gonna talk individually about each stages we're gonna use. We have used in this implementation. The first is patch variance, and the patch variance, it's calculate variance is quite a computational task, and in order to increase the performance of this algorithm, the author designed a technique that uses integral image. The EP squared minus EP is the variance equation, and we can notice that the EP squared can be computed with integral image in constant time, and so does EP. So the integral image is used in this example so as to improve efficiency of this algorithm. And the patch variance level, you're gonna have to figure out 50% of the points. And then the next stage is to let the remaining points go through the ensemble classifier. The ensemble classifier uses a random forest as the basic classifier for this job. The random forest consists of n-base classifiers, which are called trees or ferns. Actually, also in this implementation, it uses ferns, and each trees perform pixel comparison. And the pixel comparison is like you randomly choose a dozen. In this case, it's 13 points in one pixel frame, which in the frame of the object is within the object boundary. You choose 13 frames, and you just in another frame you have scanning window, and you just match the newly these points in the new frame and match with the previous frames and find the binary code. How to generate this binary code? It is like this. For example, for each point you choose its neighbor. It can be either 4 neighbor or 8 neighbor, and the neighbors can you have each point's neighbor, so you have the distribution of these points. Either the left corner one is larger than the gray I mean the gray value. The left corner one is larger than the right corner, or left side is larger than the right side, and the kind of stuff. And you have this relationship, and you're gonna have to output this binary code in this manner. And this binary code is continued to sent to the posterior probability to calculate the posterior, which can be used to determine if this patch is rejected or accepted. So if this posterior probability is larger than 0.5, you will think this patch is accepted, which should be going to the next stage. Otherwise, it could be rejected. So in the next stage, there are only a couple of few patches remain. So just do the nearest neighbor comparison. And a patch is classified as object if there is some certain kind of similarity matrix, such as correlation, is larger than 30, the certain threshold. You're gonna regard this patch can be accepted, and you finally output this patch in this stage. Now you have the detector's output, and you also have the tracker's output. So what the integrator does is to combine these two results and give the final results of the tracking. The process is like it outputs maximally confident result either from tracking or detection. If none of tracking or detection nor detection has given out certain results, you just declare the object as invalidable, so you do nothing. So we just have talked about two major parts of this algorithm, which are tracking and detection. And the learning part, the learning component is also very important in the algorithm, because it can help the detector to make better classification. So I will talk about this learning in the next few slides. The objective of this learning component is to evaluate and update object detector. And in this implementation, there are two kinds of experts that are used in this implementation, which are called P-expert and N-expert. The P-expert just generate positive examples, and N-expert generate negative examples, as discussed in this paper. So we're gonna see from this diagram that this P-expert, the P-expert generate positive examples, and N-expert generate negative examples to the training set. and this training set will fed into the detection stage for training, and you finally get the classifier parameters. And the unlabeled data will go through the classifier and get the classified results. And the classified results, there are certain kind of misclassification could happen, so you have to let it go through the PN experts. When the PN experts identify certain misclassification, and you will let it go through it and correct the results and send it to the training set as the correct label. So this is a diagram of how this peer learning works. And as we mentioned before, the p-expert at positive examples, it just explores the temporal structure, the trajectory to discover new appearance of this object. And if the detector labeled the current location as negative, the p-expert will generate positive samples. The working diagram is like this. First, you have a couple of points, which are positive examples, and you add a new example to this training set, and the p-expert is going to help to identify the reliable path of this trajectory and correct the wrongly classified results and add it to the positive training set. And the n-expert does the opposite. It assumes the object can only exist at the most at one location, and it also analyzes patches returned from detector and tracker. Patches not overlapping with maximally confident patch are labeled negative. So the method is pretty simple. You just choose the patches from the surrounding of these positive patches, and you regard it as a negative patch, and you continue. You just keep adding it to the training set. That is how the n-expert do. And also there are some kind of stability issues that needs to be considered. First is PN experts can make mistakes themselves, and the authors actually made some solid, decent job in improving improving the results. That if the error rate is less than 0.5, the peer learning will finally converge, and this algorithm will become stable. Yeah. So actually, there are certain kind of things that we've left, which is the object model. We can see that the TOD framework has an object model that consists of positive samples and negative samples, and the PN experts just keep adding these samples to this training set, and this whole thing consists of this object model. Because in every frame, when you do detection or you do tracking, you're gonna use this information to help you determine what's the best results you're gonna achieve. So I have talked about all these three frameworks. We've been talking about tracking, learning, and detection, and all these three works. They just the detection can do jobs like updating detector, and the learning can provide the parameters that can be used in detection. And when a video frame, just the first video frame comes, it goes through these three steps simultaneously, and the output, it has to be gone through the integrator, and you finally get the object state. So this is how the TOD framework actually works. Okay, let's see a demo of how this algorithm can work. Okay, let's just take a look at. First, you have to choose the bounding box, and the algorithm starts tracking, and you know, it like yeah, you can see it's pretty robust, and when you shake your head, you can also you know, it's like you you know, it can track accurately. And also you can add some noise or things like that, and our algorithm will work pretty good. Yes, currently it works pretty good. And you can do a scaling back, and you can also do like fast changing your motion, object changing fast, and the trackers works pretty well. And partial occlusion also can be handled. You know, the partial occlusion, yeah, it's pretty good. It handles pretty well. And yeah, you might have noticed there is a little drift, but it doesn't matter, because you know, this is caused by the learning, which keeps adding new samples. But the problem is you cannot ensure that all samples you added were pretty you know, all samples you added are pretty accurate. So sometimes it just happens you're just adding some of the false, you know, some of the false examples, and this will make the algorithm drift. And it's yeah, it's pretty stable for a couple of minutes. And but another thing you can notice is the frame rate is dropping a little bit. Okay, we have finished the demo. So the next thing is I'm gonna show you is this the code. Yeah, the MATLAB code, and you know, let's run it, and you know, yeah, yeah, it runs pretty good. And then the first you're gonna have to choose a bounding box, and you double click it, and you can see this is a real-time tracker. It can track your motion, because you know it's evening at my house, so the lighting condition is so good. You can see the algorithm just lose some sort of accuracy, but it also pretty much, you know, pretty much accurate, robust. And the partial occlusion also, I keep, you know, keep shaking hands pretty fast, you know, it can handle this problem. And also you change appearance, like drinking water, nothing. It seems the algorithm works pretty good. You like drinking water? Yeah. And you create some noise, partial occlusion, and you can even make a phone call, and you know, you just rotate your face a little bit. Yeah, you know, you can see the algorithm tracks very well. And partial occlusion, nothing happens, and you know, it's pretty good. Okay, so I think I've done with this presentation. Yeah, hope you enjoy it. Okay, thank you very much for watching this video. I appreciate it. Thank you. Goodbye.